This is part 1 of Unit 6, Lesson 8, Advanced Integration. In this section, we're going to be discussing how to integrate some mostly transcendental and related functions, especially when they're paired with an algebraic function. So just to review, here is all the trigonometric functions and their antiderivatives that we have developed over the last couple weeks. And we've learned using u substitution and other techniques how to find secant and cotangent and tangent. So they're all listed there. So now the next part has our logarithmic and exponential functions that we've been working with. And then, of course, our inverse trig functions as well. These come up sometimes, and of course, you can use some integration techniques to find their antiderivatives, but it is helpful if you remember what they are, especially these 6. Okay, now sometimes you might need to rewrite or rearrange your integrals that have squared terms. So, of course, the first line here is our Pythagorean identities, and then our double angle identities are listed below. Remember that cosine has a couple forms you can use it as. So there's 3 different forms you can write it. And then, of course, you can also write cosine squared and sine squared in terms of cosine 2x, and sine 2x's identity is listed there as well. Sometimes it is helpful to go back and forth between the two. All right, so let's practice using those a little bit with some of the techniques we already have. The first one is an inverse trig, and we haven't done any of those antiderivatives yet, so let's start with that. You want to recognize this as a form of the derivative of inverse tangent. So remember that from the other page, d dx of inverse tan of x over a, because the ones we've done in the last few lessons, a has been 1. This is equal to 1 over a squared plus x squared. So what we want to do and what we have here is realize that we have an a squared of 5, and I'm going to call it u squared of 4x squared. So then when we do our u substitution here, we can let u be 2x, and I'm just going to write over here that a is going to be the square root of 5, because we're going to need that. And then, of course, du is 2 dx, and we need to take away that 2. So we're ready to write our integral. So we have 1/2 the integral of du over, I'm going to write it this way, square root of 5 squared plus u squared, and that is going to be, of course, 1/2, or 1 over the square root of 5, and then the inverse tangent of u over the square root of 5. So doing our substitution back, we have 1 over 2 root 5, and then we have inverse tangent of 2x over the square root of 5, and of course our plus c. Now that one you didn't need to do a u substitution for, but it was just easier to see the inverse trig derivative there using the u. Okay, same with the next one. This is another inverse trig one. We have inverse sine right in the numerator, and its derivative is right in the denominator. So this is a pretty straightforward one. So u, we're going to let equal inverse sine of x. So du is going to be the derivative of inverse sine, which is 1 over the square root of 1 minus x squared dx. So our integral just becomes u du. So when we integrate this, we get 1/2 u squared plus c. Substituting for u, we get 1/2 inverse sine of x squared plus c. Okay, I just wanted to do a couple of inverse trig ones because we had done a couple inverse tangent, but they always had one as a. Okay, so now we're going to look at another integration technique, which is called integration by parts. So as we talked before, we needed use substitution because of the chain rule. Integration by parts helps us find antiderivatives from the product rule. So, and as I've noted here, this is usually used for products of algebraic and transcendental functions. So the formula for integration by parts is, now we're going to have two different functions. We're just calling them u and v, and they're differentiable functions of x. So you have u, this is what you're looking for when you originally get the problem, is a form of u v prime dx. And how we're going to write it is, we're going to write it in this way. We take uv minus the integral of u prime v dx. So the easiest way to see this and how we work through this is in this form right here. This is the form I'll be using mostly. So when you go to integrate this, you get uv minus v du. Okay, so how do you go about doing this? So the first thing you want to remember is, let dv the more complicated part of the integrand, but it should be something you can easily integrate because you're going to have to integrate it. Then ub, the simpler derivative one. So you want to make something that it's going to make the entire problem simpler when you take the derivative, not more complicated. Use this form to decide how to pick your u. Liate is what I always say. So if you have a logarithmic, make that your u, and then an inverse trig, then an algebraic, then a trig, then an exponential. And the nice thing is, if you start it and you get yourself into a hot mess, it's no big deal. You're just going to have to start over. And the nice thing is, if that one doesn't work, just switch it, because there's only two functions. If you pick the wrong u, then it has to be v, and vice versa. Okay, so how does this work? The first couple are pretty straightforward, so it'd be nice to get the formula down so we can go through this. My husband got a cuckoo clock for Christmas. All right, so we have the integration of x e to the x dx, and so we have to decide what our u and v is. And based on our liate, I am going to make u be x, and dv is going to be e to the x. And so when we integrate, well, first we're going to take the derivative of u, so du is going to be dx, so that's much simpler. And v is just the antiderivative of e to the x. So now my integral becomes uv minus the integral of v du. And then I just substitute all that in there, and I find the value. Okay, so u is x, v is e to the x, and from that I'm going to subtract, finding the integral of e to the x dx. So this becomes x e to the x minus e to the x, and of course plus c. So there, that's the basics of using integration by parts. Okay, so for letter B, you have one function here, and this is really how we find the integral of ln of x, which we've kind of avoided a little bit. So it looks like there's only one function there, but we can put a second function in there. So what we could do is we can let u, following our little liate formula, ln of x, and we can let v be really just the dx, or 1. So when we take the derivative of u, du is going to be 1 over x dx, and when we, this is dv, I'm sorry, and when we integrate dv, we're just going to get x. Okay, so using our formula, so we're going to have uv minus the integral of v du. So u is ln of x and v is x, so I'll write it as x ln of x minus, and now we're going to integrate v, which is x, times u, which is 1 over x dx. So this becomes x ln of x minus integral of dx. So we get x ln of x minus x plus c. Okay, so continuing practicing this, but now putting it into definite integral form. When we did u substitution, we talked about the fact that you can just change the boundaries of integration and then substitute for u. In this case, it's just going to be easy to do your uv, and then everything will be in terms of x, so you don't have to change your boundaries of integration. So in this case, we are going to let u be x and dv be e to the negative x dx. So du is going to be dx, and v is going to be, we're missing a negative here, negative e to the x, e to the negative x. Okay, so then using our formula, so we have uv minus the integral of v du, we get x, and we need that negative in front for the v, and then minus, and whoops, and then we're going to have the integral of negative e to the negative x dx. That's our du. And we really should here, to be good mathematicians, put 0 to 4 there and 0 to 4 there for our boundaries of integration. Okay, so now we have negative x e to the negative x, and this is going to become plus, and we're going to have a negative e to the negative x, and this whole thing now is going to have the boundaries from 0 to 4. So this is going to equal, when I do that, I get negative 4e to the negative 4 minus another e to the negative 4. And then when I put 0 in the first one, I get 0. And then when I put 0 in the second one, I'm going to get a negative, a 1, and then it's going to be negative because of the negative sign. Okay, so simplifying this, I get these two add together. So I get negative 5 over e to the 4th plus 1. Okay, letter D. How to decide here which one? Remember our Lie8, so we're going to let u, whoops, we're going to let u equal ln of x, because in our Lie8, logarithmic comes before algebraic, and dv is going to be x to the 3rd dx. Okay, so taking the derivative of ln of x to get our du, we get 1 over x dx. And then to integrate x to the 3rd, we get v to be 1/4 x to the 4th. Okay, so now using our integration by parts, we're going to have uv minus the integral of v du. We get 1/4 x to the 4th ln of x. That doesn't look like a 4. And then we're going to have minus the integral of 1/4 x to the 4th over x dx. So rewriting that, we get 1/4 x to the 4th ln of x. Oh, and we need this, of course. 1 to e 1 to e minus 1/4 integral of x to the third dx. So that's going to give us, and this is again from 1 to e, 1 to e. So this is going to give us 1/4 x to the fourth ln of x, and then we're going to have minus 1/16 times x to the fourth, and this whole thing is going to be evaluated from 1 to e. Okay, so going ahead and doing that, we get, putting e in, we get 1/4 of e to the fourth minus 1/16 e to the fourth. I'm having trouble with my fours today. There we go. And then from that, we're going to subtract what we get when we put 0 in. And of course, ln of 0 is 0, so that first term will disappear. So then we'll have a negative, we put 1 in for x there, a negative 1/16. Okay, so simplifying this, we get our final answer. Combining these, they're like terms. 3/16 e to the fourth plus 1/16. And if you want to write it this way, 3e to the fourth plus 1 over 16, you sure can. Okay, so the last part of integration by parts is sometimes you might need to do a u substitution, and also what happens if you have functions that whose derivative don't simplify things. You find yourself, you're in a big circle. So we're going to do like successive integration by parts. So that's what this last part of this video is going to be about. Okay, so for this one, what we want to do is we want to do, we're going to start it just like we normally did, but what we're going to see in the middle is we're going to need a u substitution in the middle. So for this one, this is an inverse trig, so that's going to be my u, and I'm going to write it this way for space. So dv is going to be my dx. So when I take the derivative of inverse trig, du is going to be 1 over 1 plus x squared dx, and v is just going to be x. Okay, so using our integration by parts form, we get our u, which is inverse tangent times our v, so I have x inverse tangent of x minus, and now we're integrating x over 1 plus x squared dx. Now here is where we're going to have to do a u substitution, because that turns out to be a chain rule problem. So normally we don't use u again because we're using it for u and v. So just to make our lives easier, what we'll say here is we'll let w equal 1 plus x squared. So dw is going to be 2x dx. So divide by 2 here. And we have what we need here. So our integration looks like this now. We still have our x inverse tangent of x minus, but now this part is going to become, we have our 1/2 here from that, and then we have dw over w, because here's the w, and then the dw is that, which is our x dx. Okay, so that's pretty easy to integrate. That's just our ln of x. So our final form becomes x inverse tangent of x minus 1/2 of ln of, and I'm just going to go ahead and substitute our w in there, which is our 1 plus x squared, and then we have our plus c. So sometimes you might have to do that in the middle. Now, for letter B, there's a little trick here to this one. And what that trick is you just might want to rewrite it to begin with. So what you want to see is that you have the square root of x in the exponent of e. So what if you let w, we're using w because we have to do a substitution here, equal that, and then if you look in terms of w squared, then we have an x, so we can easily get a dx, which is what we want because that's what's in the original problem. So now we can take the derivative of w squared, so we get 2w dw is going to equal dx. So our integral now looks like this: e to the w times 2w dw. All we did was a bit of substitution there. Okay, so simplifying this a little bit, let's take the 2 out, and then we have e to the w dw. So now we can do our integration by parts with w. So we'll let u equal w, and dv is going to be e to the w. So when we take the derivative of w, we get our du, which is dw, and when we integrate dv, we just get e to the w again. So now we're in good shape here. So it's going to be uv minus the integral of v du. And so we get our u is w, our v is e to the w minus, and we're going to be integrating e to the w dw. So we get w e to the w minus e to the w. And then of course our plus c, which we're going to put back in. So our final answer is, and shame on me, I lost the 2 from here, so there should be a 2 around this whole thing. So I'll fix that. So when we go to substitute back, we're going to have the 2 times w, which is square root of x, e to the square root of x, minus 2 times e to the square root of x, and then plus c. Okay, now how about successive integration? Here is the key though. Make sure once you decide which function you want to use for u and which one for dv, don't switch it out when you realize you have to integrate by parts again. Don't say, oh, let me switch it, maybe it'll be better. It works out if you keep it that way. So for this one, I am going to let, using our rules just like we did before, I'm going to let u be x squared. And because remember, in our little lie 8, algebraic comes before trig, and then my dv is going to be cosine x dx. So my du is going to be 2x dx, and my v is going to be sine x. Okay, so let's go ahead and do this. So I have uv minus the integral of v du. So u is x squared, v is sine x, minus, and then I'm going to integrate sine x and du. Let me make a little room here. So here's my sine x. My du is 2x dx. So I have the 2 there, and I have to put the x in there. So what I've done is I've created another, right here, another integration by parts. So this is what I'm saying. We've left, in the first one, our u was our algebraic expression. So keep it your algebraic expression. So what we're going to do now is we're going to say from here, we're going to let u be x and dv be sine x dx, so that my du is dx, which is great because now I'm going to eliminate the need to do it again because I'm just going to have a dx. I don't have a second algebraic function. And my v is going to be negative cosine x. Okay, so now here's what my function looks like. I have my x squared minus, my x squared sine x. and then minus 2 times, and now I'm going to have a uv times the integral of minus the integral of v du. So my u is now x, my v is now negative cosine x, and then I'm going to have minus, and then I'll have minus the cosine, so that'll become plus the integral of cosine x dx. Okay, so that's pretty simple to do then. Then I have x squared sine x from our original part, and then I'm going to have plus 2x cosine x minus 2 sine x plus c. So that's not too bad if you have to do it twice. But there are times when you have to do it more than twice. So what do? So there's this nice little table you can do, and it makes it easy. You label one column D, because this is the D for derivative, so this is where u is going to, you're going to take the derivatives of u here, and I for integration, so this is where you're going to integrate dv. Okay, so we're going to start by writing what we have. So u is x to the third in this equation, and dv is e to the 2x. And I'll get to what those plus and minuses are in a second. So now what we're going to do is we're going to go take the derivative of u, hopefully till we get to 0. If it doesn't go to 0, we're going to go till what we're going to find out is that we're going to recreate the original problem. And we're going to do one of those in the next example. So I'll get back to that in a minute. So this is going to be 3x squared. Then I'm going to have 6x, then I have 6, and then I have 0. Okay, now I'm going to integrate e to the 2x successfully. So I'm going to have 1/2 e to the 2x, and then 1/4 e to the 2x, and then 1/8 e to the 2x, and then 1/16 e to the 2x. Okay, so here's how this works. Now what you do once you have that is you're going to multiply along the diagonals, and that's why I have those arrows there. I have those arrows there. So we're going to multiply these terms together right here. This one we don't need because that's dv, and we don't use that. Now what the signs are here for is you're going to alternate the signs, because in our formula, let me write it over here, you have that minus sign there when you integrate v du. So it's going to alternate. Every time you redo this, you're going to have that negative in there, so it's going to distribute through. So it's going to alternate the signs of each successive integration by parts. So the first term is going to be right here, so I have 1/2 x cubed e to the 2x, and then the next term is right here, so then minus, because now the second term I'm alternating, this one was positive, so the next one will be minus 3/4 x squared e to the 2x, and then up here I'm going to alternate signs again, plus 6/8 x e to the 2x, and then the last term is going to be minus 6/16 e to the 2x. Now, I just like to simplify things, so this is going to be 1/2 x cubed e to the 2x minus 3/4 x squared e to the 2x plus 3/4 x e to the 2x minus 3/8 e to the 2x, and then of course plus c. Okay, it seems like a lot, but when you put it in a table like that, you can keep everything very organized. And how that really helps is when we go with, for the last one, is when we use a table. Well, actually I have two more here. When, you know what, I'm going to leave this one for you guys to do. I didn't put as many as many details in the table so you guys could figure out how many rows you need and the signs and everything. So you guys try that one, and I'll write the answer here. Okay, there's the answer to example 6. We can go over this in class if you did not get that answer. Okay, one more example. I know this video is a little long, and then the next video we will do partial fractions. Okay, just a little note here, and that note is that, as I was saying before, you might find that you're in an endless loop. Because if you look at example 7, e to the x is its own derivative. You're never going to get to 0 if you choose that as u. And cosine x is a derivative too that goes back and forth between cosine and sine. So at some point, you're going to end up, hopefully, with your original integration, and then there's a little trick you do with that. Okay, so let's set up our table here. So here is my d and my I and then my sines. Okay, so I'm using e to the x for d, and then I'm going to use cosine x dx for my dv. Okay, so my first term, I take the derivative the first time, I get e to the x, and of course, let me just write this down here so I have it. So then when I take the derivative of e to the x, I get e to the x again. And when I take the derivative of cosine, I get minus sine x. And then when I take the derivative of e to the x, I get e to the x again. And then I'm going to take the derivative of minus sine x, and I get minus cosine x. And of course, this will be plus, minus, plus. Now here, right here, you want to stop. And the reason for that is, look what you have here. You have the original function with a negative sign. So here's what we have so far. We have our integral of e to the x cosine x dx. And let's write it out what we do have. So along our diagonals, we have this. We have negative e to the x sine x, and then we're going to have a we'll have a double negative here. We'll have minus and then this negative here. So then we also have plus e to the x cosine x, and then we're going to have to take the derivative again. So we're going to end up with minus the integral of e to the x cosine x dx, because we're going to have to do this again. So we haven't finished the integration. So here's what the little trick is we can do. What we'll do is we'll add this to the other side, because it's an algebraic expression. We'll put it with its like algebraic expression. And so now we have two of these. And so we're left with our other two terms that we already integrated. And what we can do now is, this is a constant, divide both sides by 2. So we have solved that e to the x cosine x dx is equal to this algebraic expression right here. So if you want, you can leave it like that, or you can rewrite it like this, negative 1/2 e to the x sine x plus 1/2 e to the x cosine x plus c. Oops, sorry, went off my screen. So move this over a little bit. So plus c. Okay, so we made something that looked super complicated into a very quick problem by recognizing that we were going in a loop, and when we get to the loop, we can set it up in this way to simplify the work. Okay, as I said, this video is already long. I'm going to finish with our last integration technique for this section on partial fractions in the next video.